What is identity? It's the do nothing. Okay? So, with addition, if I take a 3 and I add the identity, it does nothing. What goes in the blank? 0. So, the additive identity is equal to 0. Because when I add 0 to any number, it does nothing. Does that make sense? What about this? 5 times the identity does nothing. So the do nothing for multiplication is what? Equals 1, right? I can take any number I want, multiply it by 1, and it does nothing. Okay? That's identity. Now, inverse. What's the definition of inverse? This is our definition of identity. It's the do nothing. No matter what operation you're using, no matter what elements you're using. Here we're using the numbers, but inverse. The element, I'm going to put, it could be a number, but it could be something besides a number. Those of you who have had Algebra 2 and have done matrices, there is a identity matrix. When I multiply a matrix by the identity matrix, it does nothing. Okay? Matrix isn't a number. We're going to call it an element. The element that yields the identity. That's our definition. The number that gives us, that equals the identity. So, if I'm looking for, let's just use 3 again. 3 plus something. I'm looking for its inverse. The inverse will be the number that yields, that gives us the identity. What's the identity? 0. The additive identity is 0, so the inverse would be the number that would give us that. What number goes in the blank? -3. So the additive inverse would be described as what? -3 for this one. But what would be the additive inverse of 7? -7. The opposite, okay? So the opposite is the inverse when we're adding, because it will always give us the additive identity of 0. Does that make sense? Let's try 5 again. 5 times some number. If this is the inverse, then this number here, this element here, will give us the identity, which is 1. What number goes in the blank? 1/5. So what would the multiplicative inverse of 7 be? 1/7. What would the multiplicative inverse of 2/3 be? 2/3 times what will yield the identity? 3/2. So the multiplicative inverse is nothing more than what? The reciprocal. Does that make sense? All right. Why is that important? Why even know about it? Anybody have any ideas? We learned back in the last unit that if I had -2 minus a -3 equals, how do we do this? Well, we can do it with chips, and we can do it with hot and cold cubes, and we typically, what do we do? Right? In other words, subtraction is just like adding the additive inverse. The definition of subtraction is adding the additive inverse. And so, that's how division has been defined as well, right? So, if we take 2/3 divided by 5/2, what? That's the same as, so division is just like what?
2/3 times 2/3.
Multiplying by the multiplicative inverse, which is, right? But why does that work? And how do you teach it to kids? What were you taught to do this? What did your teacher say?
I must keep, change, changed. Just how do I...
Keep, change, change. I've heard keep, change, flip.
We always did copy, dot, flip.
Copy.
So you copy the
Okay,
first
so
one,
you copy,
dot, so like
dot.
like
copy, dot, flip. So your teacher taught copy, dot, flip. But why? How? I mean, that's just a trick, right? Does students have any kind of reason why that should make sense? Other than, here's the way it is, kids. In fact, I have heard teachers saying, yours is not to question why, just invert and multiply.
Well, you kind of need to do it because the fractions are already numbers being divided, and so if you can't really divide again by a divided number. If that makes sense.
Can't divide again by a divided number. Oh, you can't divide by a divided number?
Yeah.
So, how do you teach division of fractions so that it makes sense to kids? You know what an advocate I am on making sense to kids, right? We're going to spend some time today doing that. Did that answer your question? We
Yes,
kind of got.
I think I forgot the first part,
beyond
and
the-
it says yields the identity, so I was like, well, that's the inverse then, because it's 1 on the end, the identity. Anyway, I just flipped them because I thought that they both looked like the identity.
Gotta be the right identity.
The element, yes. Yeah.
It's gotta be the right identity.
Yeah.
0 for addition, 1 for
And I knew
counts.
one was the multiple one.
Yeah. Morgan?
I think I have a way to like kind of prove why that works. Like invert multiply.
Yeah?
Yeah. Can I show you?
Sure.
Okay. Like we're talking about the identities and stuff, we realize like, talked about this in another class of mine. He said like, alright, if you have 2/3 divided by 1/5, we know that like, just from learning, like we know that you can change that into 2/3 times 5/1. And so like, when you think about it, the reason that would work is because like, 5/1 times 1/5 is just gonna be 1. Does that make sense? And so like, when, like, alright, so we set it up like, we had 1/5 times like something like A equal 2/3. Like to solve that, you would multiply this by 5/1, and you would multiply this by 5/1. And that's why like, does that make sense? I'm having a hard time trying to explain it, but do you see what I'm trying to say? Like,
She's taking this statement right here. Where did she get it? Yes. Here's the problem. 2/3 divided by 1/5. I don't know the answer. We'll call it A. That and this are in the same fact family, right? This is the division model of the missing addend, right? Can everybody see that? They're in the same fact family. And then you use principles of algebra
yeah.
to show that this cancels, right?
Yeah.
Leaving A equals 2/3 times 5/1.
Yeah.
Does that make sense? There's another way we could look at it. I think this is helpful. I could take this original problem and say that's the same as 2/3 divided by 1/5, correct? Do you agree with me? I mean, this is the same as that?
Yeah.
All right, what happens when I multiply a number by the number 1? Nothing, right? It's the identity. So I'm going to multiply this number by the number 1. I think you would agree with me that this 5/1 divided by 5/1, that's the number 1, is it not? So if I've taken a number and multiplied it by the number 1, I should get the very same number that I started out with, right? Well, that is going to be 10/3/1, which is 10/3. So, do you see how I ended up with this times the reciprocal of this? There's another way to think about it. But there are even more basic ways of thinking about it, and we're going to approach those in just a minute. I need to find out if anybody's got questions about the area model for multiplying fractions. Yes?
I understand how to do it. I was just confused when it's like a whole number in front of it. How does that
A whole number in front of it? Like what? Let's just take 2 and 1/3. times 1 3/4, right? So you've got your grid paper out there. And down here, since this is thirds, I'm going to do 1, 2, 3, there's a hole. 1, 2, 3, there's 2 holes. 1, 2, 3, there's 3 holes, right? And I want to come down 2 and a distance of 2 1/3. Where's that? 1, 2 1/3. So I'm going to shade this all the way over like this. So there's the width, 2 1/3 times the length. Well, that's going to be in fourths, so I'm going to go 1, 2, 3, 4. There's my 1. 1, 2, 3, 4. There's my 2, right? And I want to shade how much? 1 3/4. That's right there. So I'm going to shade right over to there. Now, where do I find my answer? In the intersection. So where the shading is overlapped. Where's that? Right inside there. Everybody see it? That is my answer. It's 2 1/3 by 1 3/4. This distance 1 3/4 here. It's an area model. How do I get my answer? Well, if these here are divided into thirds, I need to identify what my unit is, what a whole is. A whole is 1 by 1. 1 by 1. This is a whole. Man, cheap chalk nowadays. Snaps in your hand. That's a hole. Well, I've got at least one hole because it's double shaded there, right? But how many little squares are inside there? 12. So I have 12 12s here. Here is another 12 12s. So I've got one hole right here. Here's 2 holes. And then I've got this little bit outside of here and this little bit outside of here, right? Now what I can do is I can take these 3 and put them over here and finish filling in these 3, right? And now I've got a third hole. Then I can take these 3, right, and put them in right here. And now I've got a fourth hole, and what's left over? 4 and 1 what? 12 should be my answer. We didn't do any kind of algorithm, we just looked at it. Is that the right answer, by the way? Better be. 2 1/3 times 1 3/4. We get, there's several ways to do this problem. Let's do it the way your teacher probably taught you. What did she say to do, or he? Most likely a she. Improper fractions. 7/3 times 7/4. And we end up with 49/12. But 12 goes into 48 4 times, and then there'll be 1 left over, which is what we said we got from our diagram, right? That's one way to do it. Anybody know another way to do this? Well, do you agree that 2 1/3 times 1 3/4 is the same as 2 plus 1/3 times 1 plus 3/4. Would you buy into that? And now what I'm going to do is the distributive property, or what your teacher probably called FOIL. 2 times 1 is 2, plus 2 times 3/4 is 6/4, right? Plus 1/3 plus, oops, we've done that one. First, let's see, we need this one. That's going to be,
3/12.
the 3's cancel, leaving 1/4, right? Or you could do 3/12, which is 1/4. Now all I've got to do is add this all up, and I'll have my answer, right? Well, 6/4 and 1/4 make 7/4. So I've got 2 plus 7/4 plus 1/3. But 7/4 is 1 3/4, and that 1 will go with the 2. Now I've got 3 plus 3/4 plus 1/3. Is everybody with me? And what's this? 3 plus 9/12 plus 4/12, which is the same as 3 plus 13/12, which is the same as 3 plus 1 plus 1/12, which is 4 1/12. This may not be the simplest way to do it, but it's another way of looking at it. In fact, you can see those pieces in the diagram. This hole and this hole are the two, right? The 6/4, where do we get the 6/4 from? When we went this times this, right? Well, 6/4 is the same as, let's see, we're taking 2 times the 3/4. That's this answer right in here. That's the 6/4. There's 1/4, 2/4, 3/4, 4/4, 5/4, 6/4. So you can see those pieces. The 1/3 comes from taking the 1 times the, let's see, yeah, the 1 times the 3rd. So we'll take this 1 times this 3rd right here. There's the 1/3. And then this piece over here is our 1/4 of a whole. Everybody see that? I don't know. Was that helpful doing mixed numbers? Sometimes you have to rearrange, or I rearranged it to get whole numbers, but notice we've got 1, 2, 3, 4, 5, 6, 7 twelfths by 1, 2, 3, 4, 5, 6, 7, or 7/4, right? Times 7/3. There's the problem right there. We ended up with 49. So there's 1, 2, 3, 4, 5, 6, 7 by 1, 2, 3, 4, 5, 6, 7. That's 49 total twelfths. Can you see it that way? Okay. What else? We haven't talked about, did you read how you can use hot and cold cubes for multiplying integers? And you can also do the mail carrier problems with any multiplication, even negative times negative. You can make sense of it. But what about division of integers? How would you do it? How are you going to teach division of integers? So that it makes sense, so that they're not just memorizing rules. Anybody have any ideas? Chris?
I don't know if this is necessarily what you're asking for, but with the kids that I work with in the school districts, what I do is generally, like for the beginners, is I give them a certain amount of manipulatives, so they can be anything. And then I tell them to split them up into so many equal groups.
That's division, isn't it?
Mm-hmm.
Absolutely. So how would you represent a negative 12 divided by 4?
I have no idea.
Well, I could take 12 red chips and divide it into 4 piles. Right? And what's in each pile? 3 red chips. That one makes sense with chips. What about 12 divided by negative 3? Now we're asking, get 12 yellow ones and asking how many, what are we asking? How many piles of 3 red ones are in there? You see what the problem is? So how do you teach division with those negative numbers? Somebody said you don't? Why not try a number pattern? Get a piece of paper out, see if you can come up with a number pattern. Now, what's the rule when you're using number patterns? Start with the known, something that a student will buy into and say, yeah, I understand that, I can, and then the pattern takes them into the unknown and allows them to make sense of what might be happening. Yeah?
I have a question about that. When you like do patterns and all of a sudden you make this sign in front of them, like negative sign, are they not going to understand what that line means? That's what I'm...
They will understand what negatives are.
Okay.
They do.
So they'll just know that...
Because they have watched countdowns of a liftoff, maybe they haven't. The shuttle's not going up anymore, right?
When I taught my brother, I had to explain to him what the negative meant. He didn't know what it meant.
How old is he?
He's going into 4th grade.
Going to 4th grade. Does he play Monopoly? If people play games utilize negative numbers frequently, right? Owing money.
I have to say that we have to give credit to little kids more than we think that we can, because I taught a 5-year-old how to multiply 3 numbers by 2 numbers, and she totally understood all of it. She got it like that. She just got it.
We hope you started with concrete before you went. You
I
went right to
went
the
right
abstract.
to it, and she got it.
She's unusual.
It was amazing. I just did it on Monday, so it was great.
Okay. Anybody come up? Try to see if you can come up with a pattern for division that will take them from the known to the unknown, that will help them to develop those rules that we frequently just teach abstractly.